Imagine you're in one of those early design meetings. You're looking at plans for a huge new transit system, maybe a metro, and the projections are, I don't know, 170 million passengers a year. Just think about that scale.
Yeah, huge numbers.
Moving across this vast network, tracks, junctions, signals, your job isn't just make it work, it's make it safe, fundamentally safe. So how do you make sure safety isn't just some checklist you tick off right at the very end? How do you weave it in, like right from day one, into the steel, the code, the procedures?
That's really the core challenge, isn't it? And honestly, it's a massive professional responsibility we have in systems engineering. We're talking about flipping the script on safety, moving away from being reactive, investigating after something goes wrong.
Right, figuring out why the accident happened.
Exactly. To being truly anticipatory, trying to foresee and head off that catastrophic failure before it even gets a chance to happen. And the really sobering thing, you see this in basically every major accident report, is that most big railway failures, they could have been stopped, or at least made much less severe way back in the design phase.
And the numbers really paint a picture, don't they? I mean, you look globally. The EU data for 2023 showed, what, 805 lives lost in railway accidents? That's just tragic.
It really is.
But then you've got these shining examples like the Dubai Metro, running for over 10 years now, fantastic safety record, moving millions and millions of people. And the difference there, it's not just getting lucky, is it? It's about how they approached it.
Precisely. It comes down to methodology, specifically using two really critical link processes. First, safety and design, we often call it SID, and second, doing systematic hazard reviews. SID is kind of the big picture philosophy. It demands that you integrate hazard identification and proper risk assessment methods right from the start, as early as you possibly can in the whole systems engineering lifecycle.
So not just when you're building it.
No, much broader. It covers everything, from the initial concept sketches through design, construction, operation, those really complex maintenance periods, even right through to eventual decommissioning decades down the line. The aim is simple. Design out the risks of injury, of failure, before you've even poured the concrete or written the software.
Okay, so SID isn't just a vague idea of let's be careful. It's structured. It's about embedding safety analysis right into the system's DNA, making it mandatory. I noticed, too, it seems like SID is particularly recommended for certain kinds of projects, not necessarily everything.
Yeah, that's a good point. SID is often the go-to, sometimes even mandated, for projects that are, let's say, less complex or don't involve brand new, unproven technology. Think modifications, expansion.
Like adding more track.
Yeah. Exactly. Adding track, expanding a stabling yard, maybe buying more trains of a type you already operate. Stuff where the core system is well understood. Now, if you're building something totally cutting edge, really experimental, you'll need a much more exhaustive, bespoke, probably very complex safety case. But for these more common incremental changes, SID provides that essential, rigorous safety oversight without, completely bogging down processes we already understand well. It stops those seemingly small changes from accidentally creating big new problems in a system that was otherwise stable.
Okay, that makes sense. It applies the right level of scrutiny for the job. So if SID is the commitment, the philosophy, how do you actually make sure it happens? How do you stop it from becoming like optional homework that gets pushed aside when deadlines loom?
Yeah, enforcement is key. And that brings us to the first and maybe the most important pillar of implementing SID effectively. Lifecycle integration and safety gates. Safety can't be this separate thing happening off to the side that maybe catches up later.
It needs to be baked into the main project timeline.
Exactly. So SID workshops, these formal reviews, they were deliberately timed to happen right alongside major systems engineering milestones. Those key moments when big design decisions get locked in or when funding gets approved for the next phase.
Okay, but what's the actual mechanism? What forces everyone, engineers, managers, budget holders, to actually stop and deal with the safety aspects at that specific point?
It's the formal documentation. After each of these workshops, a detailed safety assessment report, or SAR, has to be produced, and crucially, it has to be formally reviewed and signed off. This SAR acts like a mandatory gate, a checkpoint.
A gate?
Yeah, a safety gate.
Yeah.
Without that signed-off SAR, which proves that the safety requirements for that stage have been properly addressed, checked, verified, the project physically cannot move to the next phase, full stop.
I see. So it ties safety directly to progress and budget.
Precisely. It turns safety into a commercial pressure point. If your SAR isn't ready, if safety issues aren't closed out, you might hold up millions in spending for the next stage. That provides a pretty powerful incentive for everyone to take it seriously and integrate it properly.
Yeah, that definitely stops that scenario where the engineering team just says, oh, that tricky signaling hazard, we'll sort that out later during installation, because later means no money now.
Exactly. Safety becomes a financial prerequisite for moving forward. Okay, so the second pillar is all about efficiency, leveraging existing knowledge. Look, railways aren't new. We've been doing this for a long time. The sector is mature, heavily regulated. We have literally decades of incident data, established hazard logs for common problems.
So you don't want people reinventing the wheel every time.
Right. The SiD process is designed not to waste time. We don't want teams sitting in workshops brainstorming generic risks like fire in a tunnel that we already know inside out. So a key part of SiD is using those existing hazard logs and databases as a starting point. The real focus of the workshop then becomes identifying the new risks specific to this project's scope, or maybe how this project changes existing risks.
But isn't there a danger there? If you rely too much on the old list, couldn't you miss something subtle? Like say you're adding a new comms system, you check the known hazards for comms gear, but maybe you miss how it interacts unexpectedly with the, 40-year-old power supply system.
That's an excellent point. And it's why the process isn't just ticking boxes on old lists. First, the makeup of the review team is critical. You need diverse expertise. Second, you must specifically analyze the interfaces. Where does the new thing touch the old thing? We use the existing knowledge for the known, generic threats fire, derailment due to track defects, etc. But the detailed SiD work has to zero in on how this specific design might change the likelihood or the consequences of those known hazards.
Okay, so using your example, if the new comms gear draws more power or creates more heat.
Exactly. Then you have to revisit the existing fire hazard analysis for that location. Is the current fire suppression still adequate with this increased heat load? Use the old knowledge as a foundation, but rigorously analyze the impact of the new element.
Got it. Now, the third pillar you mentioned introduces a really fundamental legal and ethical concept, especially in Europe, but really globally now. SFARP.
Yes, SFRRP. It stands for so far as is reasonably practicable. And this is, it's really the ethical core of serious safety engineering.
Yeah.
It's not enough to just scrape by, meeting the absolute minimum requirement written down in some regulation somewhere.
It's about doing more than the minimum.
Much more. You have a legal and ethical duty to implement all measures to reduce risk, unless the cost or difficulty of implementing that measure is grossly disproportionate to the safety benefit you'd get from it. It sets a significantly higher bar than just basic compliance.
And SFARP isn't just a one-time check, is it? I sense it forces ongoing improvement.
Absolutely. It creates this continuous improvement loop across the whole organization. If your SiD process for a new project identifies some extra safety control that's needed, maybe a newer, safer way to isolate equipment for maintenance, then there's a follow-on duty. You have to seriously consider rolling out that same safer control to your older legacy systems across the whole network too, provided, again, it's reasonably practical to do so.
So you can't just say, great, the new bit is super safe, but we'll leave the old bit running with the known, less safe standard.
Not if you want to properly meet your SFAP obligations. You can't knowingly maintain a demonstrably inferior safety standard on one part of your system if a reasonably practicable improvement exists and you've already identified it for another part. It pushes the baseline safety level upwards for everyone.
Okay, so that's the SiD philosophy and the pillars holding it up. Let's get practical now. How do you actually do the hazard identification? You mentioned it's staged. You can't just jump into complex maths on day one.
No, definitely not. The level of detail, the rigor of the analysis, it has to grow and mature alongside the design itself. It all starts very early on, often in the conceptual stage, with phase 1, preliminary hazard identification and analysis, usually called PHI or PHA.
Right. This is when you might literally just have sketches on a whiteboard, maybe some high-level requirements. How do you do rigorous analysis then? How do you stop it just being, a list of everyone's pet worries or confirming existing biases?
That's the inherent challenge of working with limited data. At this stage, the PHA is primarily a qualitative process. That means we're relying heavily on expert judgment, on experience, on lessons learned from similar projects in the past. We use structured brainstorming techniques like HAZID hazard and operability studies to guide the discussion.
So it's more about experience than calculation at this point.
Very much so. The output is what we call the preliminary hazard list, the PHL. This list basically defines the universe of potential bad things that could happen. It captures the broad categories of hazards we need to think about more deeply later on. For instance, if we're doing a concept study for new signaling, The PHL might include high-level hazards like incorrect signal aspect displayed or train enters an unauthorized section of track. We also try to make an early, rough estimate of the potential severity, like, is this likely to be catastrophic, major, minor? That helps prioritize where we need to focus the really heavy technical effort later.
Okay, so the PHL is like the master list, the foundation for everything that follows. Then, as the design gets more concrete, you start choosing actual components, subsystems. That's when the maths comes in.
Exactly. As the design matures, as you get more detailed information component specs, failure rate data from suppliers, how the system will actually be operated, you move into phase 2, system and subsystem hazard analysis, or SSHA and SHA. Now, quantitative methods become not just possible, but often essential, especially for any hazard that could lead to really serious consequences, like major injuries or fatalities. We need detailed modeling to prove that the risk controls we're planning actually meet the required safety targets, like the safety integrity levels we'll talk about later.
And what kind of quantitative tools are we talking about here? What gets used in SSA?
Well, the two workhorses, the most common methods you'll see are FMECA failure modes, effects, and criticality analysis, and FPA, fault tree analysis.
Okay, break those down a bit. FMECA.
FMECA is what we call a bottom-up approach. You start with individual components. You systematically ask, okay, if this specific component, say a relay, fails in this particular way, that's the mode, what's the ultimate result, the effect on the overall system? You go through every critical component, every possible failure mode, and trace the consequences. It's great for catching single points of failure where one small thing breaking can bring down something much bigger.
And fault tree analysis, FTA, you said that's top down.
Yeah, FTA works the other way around. You start with the really bad thing you absolutely want to prevent, the top event, let's say catastrophic train collision. Then you work backwards using logic gates, AND gates, or DARE gates to figure out all the combinations of lower level failures, component failures, even human errors that could possibly lead to that top event. It helps you understand the complex interactions and dependencies that could cause a disaster. Both FMECA and FTA require good data and detailed design information, and they're absolutely non-negotiable for analyzing high-risk functions.
That sounds incredibly detailed for looking at individual systems or subsystems. But as you said, modern railways aren't just isolated boxes. They're huge integrated networks. Different systems, maybe from different suppliers, all have to talk to each other perfectly. That must create its own set of risks.
Absolutely critical point. That leads us to phase 3, interface hazard analysis, or IHA. And frankly, in today's complex interconnected railway systems, IHA is often where the most critical and sometimes most unexpected risks lie. Because failures often happen not within a system, but at the boundaries, the connection points between systems.
So IHA is purely focused on those seams, those interaction points.
Exactly. It targets hazards that arise specifically from interfaces. That could be the interface between the signaling system and the train's control software, or between the main power supply and the trains themselves, or even interfaces between the technical systems and the operational procedures people follow, or between the railway and outside systems, like public utilities.
Can you give an example? Something an IHA might catch that a standard SHA on the individual systems might miss.
Sure. Imagine your standard system hazard analysis confirms the train control system is designed perfectly safely on its own. And the communications network it uses is also verified as working perfectly on its own. But the IHA digs deeper. It asks, what happens at the interface between them? What if there's a brief data dropout on the communication link, maybe during a nearby lightning strike or a power fluctuation? How does the train control system react when it gets corrupted data, or delayed data, or no data for a split second? Does it fail safe immediately? Or could that momentary glitch cause it to misinterpret a critical command or location update? It's these handshakes, these communication boundaries between different technologies, often from different suppliers, that need incredibly careful analysis. They're frequently the weakest links in the chain.
Okay, that makes perfect sense. So you do all this analysis, the PHA, the SSHA, the IHA, you identify the hazards. Now you have to decide what to actually do about them. How do you choose the right fix?
Right. And all that analysis work feeds directly into deciding on the risk reduction measures. And for that, we use a fundamental framework called the hierarchy of controls. This is probably the single most important concept in practical safety and design. It ranks control measures from the most effective down to the least effective.
And the goal here, the ideal, is always to design the hazard out completely if possible, to rely on robust engineering, not on people always doing the right thing under pressure.
Precisely. That's the ultimate aim, inherent safety. So right at the very top of the hierarchy, the most effective level is level 1, elimination.
get rid of the hazard altogether.
Exactly. If you can physically remove the hazard, the risk associated with it becomes zero. The classic railway example is eliminating level crossings. Instead of having road traffic cross the tracks, you build a bridge or a tunnel that's called grade separation. The hazard of a train hitting a car at that location is completely eliminated.
Any other examples of elimination?
Yeah, think about track worker safety. Historically, people had to physically walk the tracks to inspect them. Now we're increasingly using remote sensing, automated track geometry measurement systems, even drones. By using technology, you can eliminate the need for people to enter that hazardous live railway environment in the first place. That's elimination.
Okay, top tier. What if you can't completely eliminate it? What's level 2?
Level 2 is substitution. This means replacing the hazardous thing with something less hazardous that does the same job. For instance, maybe older trains used materials in their interiors that were highly flammable or produced toxic smoke in a fire. Substitution would mean replacing those with modern materials that are fire retardant and produce low smoke and toxicity. Or maybe replacing old high-voltage electrical equipment with newer, equally effective low-voltage alternatives to reduce the risk of electrocution during maintenance.
Right. And then we get to what feels like the most common type of engineered solution we see implemented. Level 3, engineering controls.
Yes, these are very common and very important. Engineering controls don't remove the hazard, but they physically isolate people from the hazard, or they use automated systems to control the hazard. Platform screen doors, PSDs, on metro systems are a perfect example. They put a physical barrier between the passengers on the platform and the track.
Stopping people falling or jumping and stopping things being thrown onto the track.
Exactly. Or think about automatic train protection systems, ATP. These systems constantly monitor the train's speed and position relative to signals and speed limits. If the driver makes an error, goes too fast, misses a red signal, the ATP system automatically intervenes and applies the brakes. It's an automated engineering control acting as a barrier. Interlocking systems in signaling are another core example. They physically prevent unsafe signal combinations or route settings.
Okay, so elimination, substitution, engineering controls, those seem like the robust physical or automated solutions. Then we move down the hierarchy.
We do. And we start getting into controls that rely more on human behavior. Level 4 is administrative controls. This is all about procedures, training, how work is organized.
Like speed restriction signs.
Exactly. Speed restrictions, warning signs, mandatory procedures for track access, rules about how long drivers can work to manage fatigue, permit-to-work systems that require formal authorization before starting hazardous maintenance. It's all based on rules and procedures people have to follow.
And finally, at the very bottom, the least effective layer.
Level 5. Personal protective equipment, or PPE. This is your last line of defense. Things like high-visibility clothing, hard hats, safety boots, gloves, eye protection. Important, yes, but they only protect the individual wearer, and only if worn correctly, and they don't prevent the hazardous event from happening in the first place.
Now here's the crunch, isn't it? We see this time and time again, not just in rail, but everywhere. Organizations often seem to jump straight down to the bottom of that hierarchy. They go for the administrative controls and the PPE first. Why is that?
Well, honestly, because it's usually cheaper and faster.
The path of least resistance.
Absolutely. Putting up a new warning sign, level 4, or issuing everyone with new safety glasses, level 5, is quick, relatively inexpensive, and it feels like you're doing something about safety. Designing and building a bridge to eliminate a level crossing, level 1, or installing a complex new ATP system, level 3, that costs potentially millions, takes years, involves huge disruption, so the temptation is always there to go for the quick, cheap fix at the bottom of the hierarchy.
But the data tells a different story about effectiveness, doesn't it? You often hear figures like 60 or 70% of major incidents having human factors as a key contributor.
That's right. And it's not usually about people being deliberately reckless. It's that relying on humans to be perfect, to always follow procedures, to never get distracted, especially in routine or high-stress situations, is fundamentally less reliable than a well-designed engineering control. Systems designed using the top levels of the hierarchy consistently outperform those relying mainly on the bottom levels.
Can we look at a real case? You mentioned level crossings earlier. That Bindara accident in Australia in 2023.
Yes. Tragically, 2 train drivers died in that collision with a truck at a level crossing. And the investigation found that the existing controls, the flashing lights, the bells, the road sign, they were all functioning correctly. Those are essentially level 4 administrative and warning controls. They were working.
But the accident still happened.
It did. Because, for whatever reason, distraction, misjudgment, the truck proceeded onto the crossing. The existing controls relied on the road user's behavior, and in that instance, it wasn't enough. This highlights exactly why the hierarchy pushes us towards higher-level controls. If that crossing had been eliminated through grade separation, level 1, or perhaps had automatic trackside barriers that physically block the road, level 3 control, that specific failure sequence likely wouldn't have occurred. When you engineer the hazard out or physically block it, you remove the reliance on perfect human behavior.
So, if elimination or high-level engineering controls aren't always immediately possible, maybe the cost is genuinely enormous, we come back to that ethical duty. SFARP. You have to justify not doing the safer thing if the risk is in that middle tolerable zone. How does an engineer, a professional, actually make that justification? How do you prove gross disproportion?
This is probably one of the toughest parts of the job. You've got your risk matrix, usually with red, unacceptable risk must fix, green, broadly acceptable negligible risk, and that yellow or amber zone in the middle, tolerable if SFARP. If your risk falls in that tolerable zone, you have to demonstrate you've applied SFARP. You need to show you've considered all reasonably practicable controls, especially the higher level ones.
And reasonably practicable means?
Generally, a control is considered reasonably practicable if it's technically feasible, if it's required by specific laws or recognized standards, if it's successfully used elsewhere in the industry for similar risks, if it's commercially available, and crucially, if the cost and effort of implementing it are not grossly disproportionate to the safety benefit it provides.
Okay, so how do you assess grossly disproportionate? Is it just a gut feeling?
No, ideally not. While judgment is involved, the best practice, especially for higher risks, is to try and quantify it. This often involves doing a cost-benefit analysis. You estimate the cost of implementing the safety measure, design, hardware, installation, ongoing maintenance. Then you try to estimate the safety benefit, usually in terms of the reduction in risk, perhaps the number of expected fatalities or serious injuries prevented over the system's life. Many safety regimes use a figure called the value of preventing a fatality, VPF, or value of statistical life, VSL, to put a monetary value on the safety benefit.
Right, so you compare the cost of the fix to the monetary value of the risk reduction.
Exactly. If, say, implementing a control costs $5 million, but the calculated safety benefit, the risk reduction monetized using the VPF is, say, $20 million, then the cost is clearly not grossly disproportionate. You probably have a duty to implement it. But if the control costs $100 million and the calculated safety benefit is only $2 million, then you can start to build a credible argument for gross disproportion. You've done the math to support your judgment.
And this is critical for everyone listening, especially early career engineers. What arguments absolutely do not work as a SFRP justification? What can you not say?
This is absolutely non-negotiable in professional safety practice. You cannot argue that a necessary safety control is not reasonably practicable simply because, quote, we don't have enough budget in our department this year, or it will delay the project schedule, or it wasn't included in the original scope the executives approved. Those are commercial arguments. They are project management constraints. They are not valid safety justifications under the SFIR principle.
So your professional duty is to assess the risk and the control's practicability based on the safety merits and the proportionality of cost versus benefit, not just based on current project constraints.
Precisely. If you decide not to implement a known, feasible control for a significant risk, you must be prepared to stand up and demonstrate, with evidence, why the cost or difficulty was truly, objectively, grossly disproportionate to the safety gain. You can't just cite budget limits or deadlines as your safety case. That won't cut it ethically or legally.
Okay, that's a really powerful point about professional responsibility. Now let's shift gears slightly. We've talked about the process and the ethics. What about the technical standards that underpin all this? You mentioned the SINELEC framework earlier.
Yes, the SINELEC standards, particularly EN 50126, EN 50129, and EN 50129, which used to be EN 50128, are essentially the gold standard globally for railway safety systems engineering. Even outside Europe, major projects worldwide adopt or adapt these standards because they provide a comprehensive, proven framework. Think of them as forming a triangle of safety compliance.
A triangle. Okay, what's the first point?
The top of the triangle, the overarching standard, is ENAM 50126. This standard defines the process for managing RAMs throughout the entire life cycle. RAM stands for reliability, availability, maintainability, and safety.
RAMs. Okay, and you mentioned earlier reliability and safety aren't the same thing. We need to be really clear on that distinction.
Absolutely. Critical distinction. They often get confused, but they can even be in tension. A system can be highly reliable, meaning it consistently performs its intended function without breaking down, but still be fundamentally unsafe if that intended function is hazardous, or if it doesn't fail in a safe way.
Give me an example of reliable but unsafe.
Imagine a signal that reliably shows a green light all the time, even when there's a train stop just ahead. The signal hardware itself might be very reliable, never failing. But the system is incredibly unsafe because it's consistently doing the wrong, dangerous thing. Conversely, you could have a system that's very safe. Maybe it shuts down completely at the slightest hint of a problem, always failing to a safe state. But if it shuts down too often, its availability is terrible, which impacts train services. EN 50126 forces you to manage this whole RAMS equation. You need acceptable levels of reliability, availability, and maintainability while ensuring safety, which is defined as freedom from unacceptable risk.
Okay, so 50126, that's the overall management process. What about the other 2 points of the triangle, the more technical standards?
All right, those are EN 50129 and EN 50717. These get into the nuts and bolts of the safety-related electronic systems themselves. EN 50129 covers the requirements for the hardware and the overall system architecture. It deals with things like hardware safety integrity, how hardware and software are integrated, and specifying the technical safety requirements the system must meet. It's basically about proving the system, hardware, and architecture are fit for their safety purpose.
And 5071C, that was the software one.
Yes, EN 5071C, which incorporates the old EN 50128, focuses specifically on the software used in safety-related systems. This is hugely important because modern railways are incredibly software-intensive. Think signaling interlockings, train control systems, even things like passenger information displays in some cases. This standard lays down rigorous requirements for the software development process itself, how you demonstrate the systematic capability of your software process, and how you verify and validate the code to ensure it's safe. It's all about preventing bugs and logical errors in the software that could lead to unsafe situations.
And when you say rigorous process for software under 50716, what does that actually involve? It must be more than just good coding and testing, right?
Oh, much more, especially for higher levels of safety criticality. It mandates specific techniques and organizational structures. For example, for critical software, it often requires independent verification and validation, or IV&V. That means the team that tests and validates the software must be completely separate, organizationally and managerially, from the team that designed and wrote the code.
To avoid groupthink or missing obvious flaws.
Exactly. Fresh eyes, independent perspective. And for the absolute highest criticality software, EN 50716 might mandate the use of formal methods. These are mathematically based techniques used during the design stage, before code is even written. You use mathematical logic to specify the software's behavior precisely, and then mathematically prove that the design is logically correct and free from ambiguities or contradictions. It's about building correctness in from the very start, rather than just trying to test bugs out later.
Wow, okay. That sounds incredibly thorough. And all these standards, this whole process ultimately leads to defining how safe the system needs to be, right? Using those safety integrity levels, SILs.
Correct. SILs are the way we quantify the required level of risk reduction or safety performance for a specific safety function. They provide discrete levels, typically SIL1 up to SETCL4. SIL1 is the lowest level of safety integrity, SIL4 is the highest.
And the requirements for SIL4, I hear they're pretty astronomical.
They are almost mind-boggling. For a system performing a safety function that requires SIL4, typically the most critical functions, like the core logic of an interlocking system or maybe parts of an automatic train protection system, it has to achieve a dangerous failure rate of less than 1 in 100 million hours, sometimes even less than 1 in a billion hours. 10 to 10 to 9 dangerous failures per hour.
Per hour? How do you even get your head around that?
It's hard. Think of it this way. It's roughly equivalent to demanding less than 1 dangerous failure in something like 10,000 years of continuous operation. It requires an incredible level of design assurance, redundancy, fault detection, and process rigor to claim SI4 compliance.
That level of rigor must surely come with a massive price tag and complexity increase. What are the typical SI levels for different railway functions?
Oh, absolutely. The cost and effort increase exponentially as you go up the SIL levels. You might find SIL4 required for that core interlocking logic, as I said. There may be SI3 for the main train control systems like ETCS. SL2 might be sufficient for things like automatic train operation, ATO systems, which handle the driving but are usually supervised by a driver or a higher level safety system. Maybe even SI1 or SI0, meaning no specific safety integrity requirements for less critical functions like passenger information systems.
And the takeaway for engineers,
The key takeaway is that achieving a higher SIL isn't just about buying slightly better components. It fundamentally changes the required design architecture. You'll need diverse redundancy, fault tolerance mechanisms. It mandates much more rigorous verification and validation processes, potentially formal methods, independent safety assessment. Going from, say, SIL2 to SIL3 for a function can easily double, triple, or even quadruple the cost associated with the safety engineering activities for that function. That's why getting your initial hazard analysis right and correctly determining the required SIL for each function early on is so critical. You absolutely must avoid over-engineering a low-risk function to SIL4, which wastes money, or worse, fatally under-engineering a critical function by only designing it to SIL1 or 2.
That really underscores the importance of that early-stage PHA and SSHA work. It sets the targets for everything that follows. This also brings us back to something you touched on earlier, this common but dangerous assumption that if you calculate the hardware reliability, the mean time between failures, then you've proven the system is safe.
Yeah, that provides a very false sense of security, because focusing only on hardware reliability ignores a whole class of failures. Railway safety engineering has to deal with two fundamentally different kinds of failure. First, you have random hardware failures.
These are things just wearing out or breaking unpredictably.
Exactly. A component reaching the end of its life, a power supply burning out, a capacitor failing due to stress. These are the failures you typically address with classic engineering techniques. Building in redundancy, like having backup systems either running in parallel or on standby, having good preventative maintenance schedules based on expected component life, selecting high-quality, reliable components in the first place.
Okay, so redundancy and maintenance can tackle random hardware failures. But then there's the other type, the ones redundancy can't fix.
Right, and these are often the more insidious and dangerous ones. Systematic failures. These don't happen randomly. They are inherent in the system due to flaws made during its creation, errors in the initial requirement specification, bugs in the software code, mistakes in system configuration, flaws in the operating procedures.
And the crucial point is, if you have two identical systems running as redundant pairs,
They will both fail in the exact same way when the specific condition triggers that systematic flaw, because the flaw is identical in both systems. Cloning the system doesn't help. It just gives you two systems that will fail together. This is often called a common mode failure when it's triggered by a shared cause affecting both redundant channels.
and we saw a truly devastating real-world example of this with the Wenzhou high-speed train collision in China back in 2011, didn't we?
Yes, that was a terrible tragedy. 40 people lost their lives, hundreds were injured. And the investigation traced the cause directly back to systematic failures in the signaling system's design, specifically in the software logic. A lightning strike initially caused a module to fail, which is a random event. But crucially, due to systematic design flaws, the system failed to revert to a safe state, like showing a red signal. Even worse, it incorrectly reported the track section as clear to the following train, even though the first train was still occupying it.
And because the backup system had the exact same software flaws.
Redundancy provided zero protection. Both the primary and the backup systems failed simultaneously in the exact same unsafe way when triggered by the initial event. That led directly to the collision. It's a stark lesson in the limitations of redundancy against systematic flaws.
So if simple redundancy doesn't protect against these systematic design or software bugs, what's the strategy? How do standards like EN 50126 and 50716 require us to deal with them?
Well, the first line of defense is incredibly rigorous quality assurance processes during development. The things mandated by EN 50716, like IV&V and potentially formal methods, trying to prevent the flaws from getting into the system in the first place. But the key technical strategy to protect against any residual systematic failures you might have missed is diversity.
Diversity, how does that differ from redundancy?
If redundancy means having two identical systems or channels doing the same job, diversity means having two different systems or channels performing the same safety function using different designs, different technologies, maybe even different teams of engineers.
Okay, how would that look in practice on a railway system?
It could mean using microprocessors from two different manufacturers in your redundant channels, or maybe having the core control logic implemented using standard software on one channel, but having a diverse safety monitoring layer implemented using completely different technology. Perhaps simpler hardware-based logic, or software written in a different programming language by a separate team. The underlying assumption is that it's highly unlikely that two independent design teams working with different technologies or methods will make the exact same subtle design error that leads to an unsafe failure under the exact same conditions. If a systematic flaw exists in channel A, the diverse channel B should hopefully catch it or continue operating safely.
That makes sense. It's like having two different experts check your work using different methods. Okay, let's shift from the potential failures to some real-world successes.
Yeah.
SiD isn't just about adding bureaucracy. You mentioned it can actually enable faster, better project delivery. The Doha Metro was an example.
Yeah, Doha is a fantastic case study. Huge project, 76 kilometers, 3 lines, built through a busy city, incredibly complex tunneling with, I think, 21 tunnel boring machines working at the same time. Massive undertaking.
And they delivered it fast, didn't they?
Phenomenally fast. From the main construction starting to full passenger service in just 7 years. And a key factor the project team highlighted was the rigorous, integrated safety management approach SiD principles applied right from day one. By identifying and resolving potential safety hazards when they were still just concepts or lines on a drawing, they significantly reduced the amount of costly and time-consuming rework needed later during testing and commissioning. It showed that getting safety right early actually accelerates delivery. It doesn't necessarily slow it down.
And then there's the long-term operational success story, like the Dubai Metro we mentioned earlier, safely carrying, 170 million people annually since 2009?
Exactly. And that sustained safety record comes directly from embedding those SiD principles and the hierarchy of controls into the core design. Think about their key features. They mandated platform screen doors right across the system. That's a perfect example of level 1 elimination, physically removing the hazard of people or objects getting onto the track from the platform. Combine that with high-integrity automatic train protection, level 3 engineering control, strict operational procedures, level 4, and adherence to international standards, and you have a system fundamentally engineered to prevent certain high-consequence accidents from occurring.
Looking forward now, how is technology continuing to evolve this idea of anticipatory safety, moving beyond just the initial design reviews?
Well, the really big shift happening right now is the move towards predictive maintenance, often powered by AI and machine learning. We're moving away from just fixing things on a fixed schedule, time-based maintenance, or after they failed, reactive maintenance, towards intervening based on the actual condition of the equipment, condition-based or predictive maintenance.
How does that work in practice?
So, for example, sensors on trains or trackside can monitor acoustic signatures, temperature changes, vibration patterns on wheels and axles. AI algorithms analyze this data stream to detect subtle anomalies that indicate a bearing might be starting to fail, potentially days or weeks before it becomes a critical safety issue.
So you can intervene before it actually breaks down.
Precisely. Similarly, automated track inspection systems constantly collect data on track, geometry alignment, twist, gauge.
Yeah.
AI can analyze this data to spot deterioration trends much earlier and more accurately than visual inspections, allowing maintenance teams to fix potential problems, like developing track buckles or geometry defects, before they reach safety limits. It optimizes both safety and cost, because you intervene exactly when needed, not too early, which is wasteful, and not too late, which is dangerous. We're also seeing it used for things like predicting points failures based on power draw and movement timing, or even using weather forecast data to proactively issue speed restrictions before high winds or heavy snow actually hit.
And technology is also changing the design process itself, not just the maintenance. You mentioned simulation earlier.
Absolutely. The use of digital twins in simulation is becoming increasingly powerful as an SiD tool. You can create a highly detailed virtual replica, a digital twin of the railway system, or parts of it. Then, engineers can use this virtual model to run all sorts of analyses before building anything physical.
Like testing failure scenarios.
Exactly. You can simulate complex failure scenarios. What happens if this signal fails, AND, the points machine fails. You can test the behavior of new software upgrades in a safe virtual environment. You can analyze the impact of different operating schedules on system capacity and safety margins. You can even use it to train drivers and controllers on how to handle rare emergencies without putting any real trains or passengers at risk. It allows for much more comprehensive hazard analysis and testing much earlier in the life cycle, significantly reducing the residual risk you carry forward into the real world.
And we are actually seeing the positive impact of these engineered safety approaches in the overall performance data, aren't we? Even though train traffic keeps increasing, which logically might lead to more incidents like signals passed at danger or SPEEDs.
Yes, while the absolute number of SPEEDs might increase with more traffic movements, the crucial statistic is that the consequences of those SPEEDs are being mitigated by technology. Recent data suggests that something like only 19% of SBDs actually result in a subsequent accident, like a collision or derailment,
Why so low?
because of those level 3 engineering controls we talked about. Modern systems like ETCS, European Train Control System, provide continuous speed supervision and automatic braking. If a driver passes a signal at danger or exceeds the permitted speed, the system is designed to intervene automatically and bring the train to a safe stop, often before it can reach the point of actual conflict. It turns a potentially catastrophic human error into a controlled, safe system intervention. It's tangible proof that robust engineering controls consistently outperform relying solely on human vigilance.
Okay, this has been incredibly insightful. Let's try and boil this down. For the engineers listening, students just starting out, or those in their early careers, what are the absolute key takeaways, the professional obligations they need to carry forward from this deep dive into SiD and hazard reviews?
Right. If I had to pick 3 core obligations, they would be these. First, fully embrace the duty of justification inherent in SFAP.
Meaning you need to know the controls and justify your choices.
Exactly. Know what controls are available, especially those higher up, the hierarchy, elimination, substitution, engineering controls. Understand what's technically feasible and used elsewhere. And if you decide not to implement one of those for a significant risk, be prepared to rigorously justify why it was grossly disproportionate. Remember, budget or schedule are not safety justifications. Your professional integrity rests on demonstrating you did everything reasonably practicable to reduce risk.
Okay, duty of justification. What's the second obligation?
Team composition. Effective hazard analysis is not a solo sport, and it's not just for the safety people. You absolutely must have the right mix of expertise and perspectives in those review workshops. You need the designers who understand the intent. You need the operators who know how it's really used day to day. You need the maintainers who know how things actually fail in the real world. You need subject matter experts on specific technologies. You need the project managers who understand the constraints. Different viewpoints uncover different hazards, especially those tricky interface ones. Don't do hazard analysis in a silo.
Makes sense. Get all the right brains in the room. And the third obligation.
Learn from history. Seriously. The best way to prevent future accidents is to understand past ones. Don't just wait for something to go wrong on your project. Actively seek out and study accident investigation reports. Understand the sequence of events, the contributing factors, the root causes, technical, human, organizational behind incidents like Bindara, Wenza, Hatfield, Ladbroke Grove, Ishida. There are unfortunately many lessons. Then ask the hard question, could that failure chain happen here, on my system? What specific design choice can I make now to break that chain before it even starts? Proactive learning is crucial.
So if we try to capture the core SiD mindset in a single thought process for an engineer facing a hazard.
It's about resisting the easy way out. When you identify a hazard, the immediate temptation might be to write a new procedure, level 4, or mandate some extra PPE, level 5, because it's quick and cheap. The SiD mindset forces you to pause and ask, repeatedly throughout the design process, wait, can we eliminate this hazard completely? Can we engineer it out? What would it actually take, technically and financially, to make this hazard impossible, or at least physically contain it with an engineering control? Always push up the hierarchy first.
That's a great guiding principle. Any final thought to leave our listeners with?
Maybe just a reflection on that constant tension you'll face between qualitative and quantitative analysis. Early on, in PHA, you're relying on qualitative expert judgment because you don't have much data. It's fast, but it's subjective. Later on, with FMECA or FTA, you move towards quantitative methods. These promise precision, verifiable numbers, SIL targets, but they demand a lot of detailed data, which takes time and effort to gather and analyze, and the models themselves can have uncertainties.
So it's the trade-off you're constantly managing, speed versus precision.
It is. And the real professional skill lies in matching the right analysis technique to the stage of the design, the quality of the data available, and most critically, the severity of the hazard you're assessing. You simply cannot accept purely qualitative expert judgment sign-off for a potentially catastrophic risk that really demands detailed, rigorous quantitative modeling and verification. Your job, fundamentally, is to apply the right level of scrutiny at the right time to provide the highest achievable level of safety assurance for every single one of those millions of passengers.
Safety in design, then. It's clearly more than just a process. It's a fundamental shift in thinking. Moving safety from an afterthought to the absolute foundation, where decisions made today in design directly shape the safety of railways for decades.
Absolutely. And for everyone listening, particularly those starting their careers, remember the power you hold. The design choices you make, the questions you ask in reviews, the rigor you apply to SiD, you are actively contributing to preventing the accidents that, thankfully, haven't happened yet.
That's a powerful place to end. That's all for this deep dive. We really hope you can take the hierarchy of controls and that SAIRP principle into your next project or study. Thanks for joining us, and we'll talk to you next time.
Thanks for listening to Safe Tracks, the System Safety Assurance podcast. Here, we talk all about how safety assurance keeps our railways running safely, smoothly, and reliably every single day. If you're curious about RAM management, RAM analysis, and how reliability is actually calculated, check out the RAMs Ready podcast playlist on this channel. It's packed with great insights. And hey, don't forget to subscribe and tap the notification bell so you'll know the moment a new episode is out. Until next time, stay safe, stay assured.